Yeah, thank you very much. Yeah, in fact, I am mainly scientist at the Rossendorf beamline of ESRF here in Grenoble in France. And in fact, Rossendorf beamline at ESRF is dedicated to actinide science. So to study of radionuclide materials by using different methods. And this is in fact what I'm going to talk today. I'm going to talk about actinides, which situated at the bottom of the periodic table. And in fact, if I compare how much do we know about actinides for compared to other elements in the periodic table, like for example, transition metals, I would say we know much less about them. And there are a few reasons for that. So the first reason is that actinide elements are radioactive. So in order to study them, one would really need to have the special facility, special chemical lab where you can synthesize and analyze those systems. But additionally, those materials contain a lot of electrons. And in fact, those electrons create a lot of troubles for theoretician to treat them and to understand them, let's say, from the theoretical point of view. But at the same time, really those electrons, those 5F electrons, so for actinides, it's already 5F shell, which is partially filled. Some actinides, 5F shell is empty. And those F electrons dictate the characteristic performance of those elements in different applications. So nevertheless, even that those electrons create a lot of trouble for us, it's still worth it to look into them and study them. So how do we study electrons and electronic transitions and electronic structure? One of the methods is, of course, to use X-ray spectroscopy. And if one make the search in any kind of database, Web of Science or Google, on actinide and spectroscopy, you would immediately realize that the most of the studies were done in the past time using L3H absorption age. And this is, of course, a really good reason for that. So the transition of L3H situated in the hard X-ray range, so meaning that you need to use hard X-ray beamlines, but hard X-rays have a big penetration depth. So you don't have to really worry about how do you confine your actinide material. So the X-rays penetrate through it, and the materials can be studied by spectroscopy. So by measuring L3H, what we do with X-ray absorption spectroscopy, we excite electron from the 2p to the 6d electronic state. And in fact, if you look at the ground state configuration of the actinides, I plotted here uranium ground state configuration. We in fact see that 6d electronic level will be empty, independently from the oxidation state, let's say. So what will be different, in fact, you will have different number of 5F electrons. And in fact, if we look at the density of states, how we distributed, I plotted here just one of the examples. This is uranium dioxide. But this is typical example where you see that 5F states were much closer to the Fermi level. So it means that in principle, they have to be much more sensitive to the electronic structure changes. So how do we probe 5F states? There are several ways to do it. So one way is to use soft X-ray beamlines and soft X-ray spectroscopy and look at the O ages and N ages. In that case, to excite electrons from the 4D and 5D shell to the 5F and study those electronic transitions. And in fact, it was done in the past time. So there are several papers about it, how you measure actinide at the soft X-ray range. The only problem here is that you might need to think about vacuum chamber and about the problem to insert actinides into the vacuum. And in fact, at the large scale facilities, if you think about the safety and safety groups and the safety officers, were generally were not really in favor of allowing putting actinides into the vacuum. So there is another way that you can avoid by having the vacuum near the actinide material is to use tender X-ray range and probe 5F states from the 3D level. So this is X-ray absorption spectroscopy at the M4 and the 5 ages. And in fact, this is what I'm gonna talk today. So I'm gonna show you how we study actinides at M4 and 5 absorption ages in the tender X-ray range. Let's look back a little bit, maybe about some history, what was really done at the M4 and the 5 ages of the actinides. And I believe the first paper published about it I found in 1987. In fact, it's a really nice review by Kalkovsky, where he reports different absorption ages of the actinides which you can record. I mean, including the soft X-ray, tender, and hard X-ray transitions. So here on the left side, you see, so this is the data, M4 and M5 at the same time. So a little bit hard to look which kind of changes we can expect. So I took one more figure from paper of Sergei Butorin in 2000. By the way, it's also the review paper, also shows a lot of different transitions, different absorption ages, and also resonant inelastic X-ray scattering data. So what you see here, this is uranium M5 absorption age recorded for different uranium compounds. They have different oxidation states, but also different compounds, different chemical compounds here. And just by inspection, you will see that in principle, all three spectra will look almost identical. So there is only one sharp absorption resonance and hardly any kind of special excitations or transitions can be seen, and this is due to the fact that core hole lifetime broadening is still in order of 4 electron volts at the M ages. So how do we go below the core hole lifetime broadening? And there is, for the moment, already well-known technique that you don't record absorption data in the standard and the classical way. You don't record all fluorescence, but you select a particular channel by choosing the crystal analyzer and X-ray emission spectrometer. So you select one emission line, and we record the excitation by changing the incident energy of the monochromator. So in that case, we are not limited in M4H of actinides. We are not limited anymore by the 3D core hole. But we already start to reduce the core hole lifetime broadening by the final state effect. In case of the M4, what we can do, we can use only one emission line. This is M beta, and that's transition from the 4F to the 3D down. And that channel can be selected in order to record data. By the way, we name it high energy resolution fluorescence detection, X-ray absorption spectroscopy, HERFD. Very strange abbreviation, but nevertheless, so this is the commonly how it's named. So I'm not going to talk a lot today about the particular method, and also not a lot about spectrometers, because definitely you can use different X-ray emission spectrometer to record HERFD data. I will go, I mean, I don't do it just because many people before me already introduced this method. And what I'd like to show you today, how can it be used in case of the actinides. So let's look at what we gain. This is the spectrum recorded for the uranium dioxide, again at the uranium M4H, and the gray curve. So this is the fluorescence channel. It was recorded, by the way, at the same time from the same sample at the beamline. And the red curve, this is the high energy resolution fluorescence detection XAS spectrum. So we see that the sharpening effect, in fact, is so dramatic that absorption feature became very, very, very sharp. And it became so sharp that you can easily distinguish between different oxidation states. So one could imagine that, in fact, if you would have uranium-6 compounds here and exactly in the same broadening like on the curve above, it will be very hard to really distinguish where is uranium-4 and where is uranium-6. Uranium-6 compound here, this is also uranyl, and in fact, that's also used as one of the examples to show how you improve resolution, but you don't see only one single absorption feature, but you really see the splitting of different states, and this is different transitions which can be analyzed in greater details. So now if I do the zoom on that energy region, so you would see, in fact, by the way, the energy difference between uranium-4 and uranium-6 here is about 2 electron volts, so that's quite a lot. And then if I do the zoom, we see that the uranium-5 that's also possible to detect, so it really comes in between according to the standard absorption rules. And where these kind of studies are useful is, of course, in cases when you would like to study systems where you expect a mix of the oxidation states. For example, one case I want to show here. So this is uranium dioxide doped with neodymium. Upon different concentration of neodymium, if you start to dope uranium dioxide, so you go away from the perfect structure of UO2 and away from the oxidation state. So you start to form uranium-5 and then uranium-6. And in fact, what is the beauty in that kind of story is that even when you have a mixture of oxidation state, the spectral profile doesn't appear as a one bump which you have to fit, and then in order to understand how many peaks you might have there, so it really comes as a separate features. And that helps if you would like to perform quantification analysis. So there are a lot of different softwares where you can already quantify how much really of the uranium-4, 5, and 6 one could have in the system. And to have this kind of resolution and that kind of separation, that of course helps a lot in the analysis. So here I want to show that example. I always show it, but here I want to show it again to point out that the reason to be able to detect different oxidation state, it's not only the spectroscopic transition. It's not only M4H as a selection versus L3. One would really need to have X-ray emission spectrometer in order to do it. So for example, here on the right side, you can see it's again total fluorescence yield recorded on mixed uranium oxides, which have a mixture of oxidation states. It was measured at the same time than the left graph. And you can see that here, I mean, you hardly see any kind of splitting and any kind of, I mean, it's less sensitive to the detection. So one would really need to have both if you would like to have this kind of studies, to go to the tender X-ray beamline, or at least to the beamline, which can reach images of actinides, but the beamline also have to be equipped with X-ray emissions spectrometer. And since that time, I believe the first experiment was done in 2009. So for more than 10 years, in fact, that idea of recording the data on uranium with a spectrometer and at uranium M4H, it was very well received by actinide scientific community, and a lot of people start to use in their research. They start to study different types of the uranium compounds and probe the electronic structure, not only the oxidation state, but also looking at the ground state configuration. Because of course, oxidation state is always linked to the ground state configuration, a number of the F electrons. So if anyone would like to really learn something or look what was really done in the past years, I put here papers which were published in the 5 years, which might be quite interesting to read in order to learn about uranium electronic structure. But let's look a little bit more careful. What do we really see, and what do we really measure by M4H spectroscopy? I show an example of uranium dioxide, and again, what I said, we excite electron from the 3D level to the first possible 5F states. And for the uranium dioxide, a ground state configuration have 5F2 electrons, so it's uranium 4+. And in principle, this is what we see in the data. So this is the intraatomic interaction of the 5F states, which create this kind of shape of the spectrum. So if one would be able to do simple, I call them simple calculation, to start with multiplet calculation, let's say, where we perform first of all calculation for the free atom. So we only take into account which absorbing atom we study. In our case, it's uranium. And then putting as an input file, you have to put the number of the electrons at the ground state. So in our case, it's 3D10, 5F2. So we put one electron up, so it became 3D9, 5F3. So already that kind of calculation will show the splitting of the absorption features. So only by this simple one step, you would already produce the main H transition and this shoulder. So it means that really 5F interactions play really the big role in MH spectroscopy, and it's definitely have to be taken into account. And then, of course, if you would like to go further and analyze, you can take into account the crystal structure around the absorbing atom or the symmetry. And as another step, you can include the charge transfer excitation or the hybridization effects if you are curious to reproduce the post-H features further, like here was done for uranium dioxide. But in fact, if anyone interested to study into in the tiny details with kind of effects of intraatomic interaction or effects of the hybridization, in fact, the best case will be to go to the simple way, let's say, or the simple element. And in our case, we thought that it's a simple case, thorium dioxide. Because thorium ground state configuration doesn't have any F electrons. So it has 5F0. And we thought that this is in principle nice example to probe the different ways of the excitation which we do observe in MH spectroscopy. But by recording the data, so here it is, so this is experimental data, this is not a theoretical approach, you will see that you also have a splitting of the main absorption feature, and even more, you get more post-H features, which in fact will be nice to understand because we look at the 3D 5F transitions, but 5F level is empty. And this is what was done by Sergey, published 5 years ago in this nice paper. So here again the red curve. So this is the experimental data, and that's what Sergey started to do. First of all, he went to the first step and just made atomic calculations because it's 5F0. So we have one electron on the excited state. So you have only one single multiplet here. So then he applied the crystal field. In case of the thorium dioxide, it's a cubic structure. So you split the states. And then the question was, okay, so we do some kind of understand the nature of force splitting, but where that kind of states further comes from. And the first step, Sergey include a charge transfer excitation between thorium 5F and the oxygen 2p states. And that was not sufficient in order to reproduce this tiny feature. By the way, this tiny feature, you only see it if you record data with spectrometer. Without spectrometer, it's almost like zero and empty. So that kind of small feature was he was able to reproduce it only by taking into account also the thorium 6D states. So it means that effects of the hybridization between the 6D, 5F, and the oxygen 2P states are quite important in order to reproduce the spectral shape. But at the same time, it was quite not common, I would say, and at least for me, it came as a big surprise that inclusion of the 6D states would really have such an effect on MH data, because 5F states on actinides were always considered as extremely localized state, so they don't really like to participate in any kind of hybridization process. But at the same time, that was a really nice example to show that in principle, this is not really the case and not always the case. So it very much depends which actinide component we study, and of course of availability of the experiments and, let's say, theories, satisfied theories which can explain the experimental spectral feature. And talking about thorium, I want to show you one of the examples of our recent studies, and that's maybe the nice example to show that in some particular cases it's quite nice to combine not only spectroscopy but to look at the other experimental methods and maybe use them in combination with spectroscopy in order to learn something. So we recently studied the formation of thorium dioxide nanoparticles, and first we thought, yeah, we record MH data and we for sure will understand everything, what's the difference between nanomaterials and the bulk system. But nanoparticles in general is quite hard to study on the way that everything, all spectral feature became broad just because of the nano effect. And then you always have a doubt, is it really the nano size or is it a crystal modification which took place? And that's why we do observe differences. So I'm talking, of course, about data here reported in the middle. So you see that features after the post-stage feature B and C, they start to disappear in case of the nanoparticles. So what we did, we went to the other beamline, to the next beamline, also ESRF, and recorded high energy X-ray scattering data, which allows you to look at the structural modification. So you can extract pair distribution function, and this is what Lucia Amidani did. So she looked at this data and she started to fit the data by using different structures of nanoparticles. And just by taking the small structure, by the way, in fact, this is really amazing method because just by one shot of the X-rays, you understand the size of your nanoparticles. And this is quite unique. So we thought that our particles are quite small, maybe 2 nanometers, but already by experimental data, we saw that they are much smaller. But even by taking the small nanoparticles, Lucia immediately realized that fit cannot be done. So it's definitely the mixture of different particles, even of small particles. So then she tried different structures and found that we have even the mixture of some kind of small clusters, hexamers. And only after she was really, she succeeded to fit structure of those nanoparticles, she used this structure for electronic structure calculations. And then she was able to reproduce the experimental differences which we observe here in the data. So, and with that, I think I can maybe stop and ask if anyone have questions before I go to exciting plutonium chemistry.
There are a few questions. First, this is a bit open-ended, so just give likely a very brief answer, is what can you say about the framework used for the multiplet calculations? Perhaps broadly speaking in the community, how are people doing those these days?
Yeah, it's, of course, there are different groups and different people. Like I mentioned, Sergei Butorin did the calculation, and he's really using his own approach and his own program. It's really based on the Cohen code, and I would say very classical way how everyone starts to do calculations. It's not super user friendly, I would say, but he is extremely familiar and extremely good of doing it. I think if you put the student next to him and someone who really doesn't know anything about the theory, that would be complicated. This is, of course, a great development in the past time was done for the Quanticode, and that's in fact what we are using now. I mean, Lucia Midani, in fact, in our group, so she's really looking towards these approaches. At ESRF, it was also developed with crispy interface on the top of the Quanticode, and that I found also quite useful. So I would say that that's maybe for people who never did the theory, that's really something nice to start and play. At least, as I said, atomic multiplet calculations, just the multiplets for the free ion comes pretty nicely from where. And I mean, of course, I think Frank de Groot is using CTM FOXAS. So, and there is another approach, TT multiplets, which was developed in Italy by Claudio Dell'Era. So that's we also used for lanthanides and actinides. So we try to play with different approaches. I mean, some people might agree, like if you would have Sergey here, he would of course say that his program is the best of the best. And I mean, of course, I have my own what I like and what I don't like, and I think that possibility to have user-friendly program that's quite important nowadays.
That's very, very true. All right, Peter Botz, you have a question?
Yes, thank you. Thank you, Kristina. That's really interesting.
Hi, Peter. Yeah.
Hello. In the experiments that you showed with neodymium doping,
yeah,
in the uranium-6 spectra, there's no oscillations that are typically seen probably from uranyl. Does that mean that in the neodymium experiments they're more like a uranate type configuration?
Exactly, you're absolutely right. So it's not the uranyl because you don't have a free structures, but we got impression it goes towards UO3. But you know, for the uranium dioxide 6+, you have also I think at least 3 different chemical configuration. One of them is UO3 alpha, beta, and gamma, right?
Okay.
So we think that it's definitely not uranyl configuration. The uranate as well. So this is one of the option, and this is one of the phase of UO3, if I remember correctly. But you are absolutely right. So it's definitely not the uranyl type structure.
Thank you.
All right, Dugan Hayes, you have a question?
Yeah, I thought it was really exciting to see that you're seeing this strong evidence for 6D contributions in the thorium spectra. And I definitely wasn't expecting that. So I'm just generally curious if that's sort of the only example you found so far, or if this is more of a recurring theme in other actinides.
Yeah, I will show you further. So we looked at the plutonium as well. So, I mean, up to now, we studied uranium, thorium quite intensively, and we moved towards plutonium maybe 2 years ago, and already have quite a lot of data. I think neptunium was studied by Tonia Vitova in Karlsruhe. I'm not sure if anything published, but I'm sure I saw several talks of your students about it. No, neptunium is published. I think I saw even the paper. And if we move further on the periodic table, I didn't see. No, maybe I'm wrong. No, I think americium was also studied at the Karlsruhe. So this is what I remember so far, but nothing else up to now. But of course, our goal is we go towards all periodic table. So we start by one by one element.
Sure. I'm wondering if you see these higher lying features that correspond to the charge transfer states that involve the 6D hybridization in other actinides.
Yeah, that's really interesting. Maybe I can show you in my next talk, because if we talk about the plutonium, everything became more exciting and you have more states where to look.
Sure. And so that'll be coming.
In fact, in the end, I have even a slide to discuss a little bit how much we have to add. Maybe as a short answer, I would say it's a bit complicated. Thorium case was clear because if you don't include 6D states, you cannot reproduce the data. But in case of uranium, for example, and plutonium, you can already reproduce all features without taking into account of the 6D states. But it doesn't mean that we're not there. You know, I mean, it just means that I also, in fact, by the end of my talk, I have a slide about it with thorium up to now giving the best possible resolution for the spectral features. And I think that's why we can really see it. So that's why I would say I still think it's there. It's only just that for the moment, maybe experimentally, we cannot really prove it.
All right, thank you.
All right. A quick question. What's the typical measurement time for the image spectra you were showing, including the XAS piece?
Yeah, that's I also have on my last slide with technical examples. So so typical time, I mean, depends of course of the beamline. So I show you most of the data. What I showed today, it was recorded at ID26 beamline of ESRF. And typical time to record data where it takes from 30 seconds till 60 seconds. I mean,
Okay.
I think it depends, of course, on concentration. If I talk about just oxides, what we study, plutonium dioxides or uranium dioxides, it's about 60 minutes to maybe maximum 2 minutes, and that's what you would already have. But if you look at the energy range, it's not so big. So it's about 12 electron volts, which what we record always. And yeah, I would say from 30 seconds to maybe maximum 2 minutes.
So full
it takes
RIX
much longer to align spectrometer than to measure.
So can you do a full RIX spectrum in about an hour?
Even less. I think
Even
it's
less.
like
Very
10,
good.
15 minutes. Yeah.
That's wonderful.
So super fast. But I mean, of course, I'm taking the extreme example of ID26. I mean, if it goes for the bending magnet beamline.
But that's okay. You're at ID26. You should take the extreme example.
Yeah, sure. Exactly.
Last question in this break is from Anatoly Frenkel.
Hi, Kristina. Nice to see you. Quick question. So I'll combine my two questions in one. So if you study radioactive elements and they decay, and assuming that you can observe that in real time during the measurement on the time scale of measurement, what would happen, for example, with a thorium oxide or some other radioactive element oxide that decays under the beam? Will you observe the new oxide structure of a different elements, or have this type of experiments been done? Like, what do you know about this kind of thing?
Yeah, it's a really interesting question. We never saw it, in fact, because I mean, unless we don't really realize it, but that will be something else to discuss. But up to now, we don't see this kind of effects of radiation. I mean, of course, we observe radiation damage, let's say, and but it's nothing to do with radioactive decay, right? So, I mean, that's two different issues. Radiation damage, definitely very often, especially for nanomaterials or some kind of special ligands, let's say. Then there are still ways how to avoid it. I mean, either we move sample around or we cool it down. And in fact, different effects can be seen. I mean, sometimes we really create different structure or different oxidation states. But it's very noticeable in the data. But I'm talking about radiation damage by X-rays, not really, I guess, what was your real question, right?
Yes, thank you very much. And thank you, Leon, for your answer on chat. Thank you. Bye.
All right, you should continue, Kristina. Thank you for taking all those questions.
Yes, thank you. In fact, I realized that I don't hear well, but maybe I change my sound later after I stop presentation. Okay, so let me move further, and the second chapter, I would say, or second part of my talk, I want to show you, or I want to show you how complex is plutonium chemistry. So, in fact, plutonium have complicated chemistry, so it exists in 4 different oxidation states under environmental conditions. Those states are changing easily from one to another one. And all 4 can be present in one particular system. And in fact, in 2006, that was also found that plutonium migrates in environment on really big distances in the range of the kilometers in form of the colloids. And since that time, a lot of studies have been done on investigation of the plutonium dioxide colloids or plutonium dioxide nanoparticles. And still there are a lot of questions which are debated between the chemists and in the literature. So I would say that 2 most debated questions for the moment is the structure of those nanoparticles. So are they amorphous or are they crystalline? And then the second question is the presence of different oxidation states. And when we started these studies, I was really surprised, in fact, by reading the literature and seeing that people claim different results. But that's, of course, have also the good reason. People make those nanoparticles under the different conditions, and they study them also under with different methods, experimental methods. So that's also apply different rules, and you also might be able to change the state of your system. So there are a lot of contradictory results, but nevertheless, of having this opportunity at the beamline to probe oxidation state of actinide materials, we thought, why don't we look also at plutonium dioxide nanoparticles? And first, I want to show you how plutonium dioxide bulk material look at the M4H's if you measure it with a spectrometer. So here's the spectrum, and you can see that the main H transition is split as well in two parts. So this is not as uranium dioxide, just a shoulder. So you really have a separated feature. And reason for that is, of course, the F electrons. So we already have 5 F4 electrons at the ground state, and this intraatomic interaction of the F states play the big role in MH spectroscopy in general. So we do have this splitting, but they all belong to the 5F4 ground state configuration. So now again, if I do zoom on that part of the spectrum, you can see that the same case as in uranium, you can see different oxidation state belong to the plutonium 4, 5, and 6. And if you have a mixed compound, a mixed valence compound, you also see all different states, even including plutonium 3. So by having this kind of opportunity at the beamline to measure M4H data, we started to, first of all, we synthesized the plutonium dioxide nanoparticles, starting from different precursor solutions. So we took, first of all, plutonium 3, 4, and 5, 2 different pH, and this is, by the way, chemical precipitation method. And reaction is really fast, so almost immediately you produce the plutonium dioxide nanoparticles. So we had 3 different solutions, 2 pH, 6 samples in total, and this is what we studied at the beamline. In fact, not only at one beamline, but here is again the combination of different methods, not only the spectroscopy at M4H, at L3H. We also use again the PDF. And the XAS and Xray diffraction, and try to combine all results in order to find out what's really do we see with plutonium dioxide nanoparticles. The first surprise was regarding the size. So all of them were 2 nanometers, independently how from which solution you start. So this is definitely some kind of preferential size of plutonium dioxide. We also saw that they're crystalline, so they're not amorphous. And the structure is very similar to the bulk, just to the plutonium dioxide itself. Regarding the oxidation state, so you can see the plutonium M4 data here. So we don't really observe difference between bulk plutonium dioxide and concluded that in principle, we do see only one oxidation state, is the plutonium 4 in all cases. But the big surprise came then we start to make nanoparticles from plutonium 6 solution. So in that case, reaction is much slow. So it takes several months before you will be able to make nanoparticles. And in fact, just by looking at the color over all this month, how the chemistry takes place, just by looking at the color, you realize that formation of nanoparticles goes through formation of some kind of additional phase, which we didn't see in any other cases when we start from plutonium 3, 4, 5, and 6. And that was pretty interesting. So we took this kind of phase during the synthesis. In fact, not really took the phase, but we thought that synthesis took place, but in fact it didn't finish. So it was some kind of luck that we were able to look at this phase before the final formation of nanoparticle took place. So we took this place and this phase, and when we measured again using M4H spectroscopy. And just by looking at the position of the absorption feature, we saw that what we have, in fact, it's the plutonium-5 phase. So this is the intermediate phase, which formed during the formation of nanoparticles. And it's definitely not 4 and not 6, so it is really a pentavalent plutonium phase. And that, of course, was also confirmed by Sergey and his calculation using Anderson impurity model calculations, where in fact he doesn't do only the multiplet, atomic multiplet calculations, but where he also introduced the effect of the hybridization. And in case of the plutonium, he went even further. So he in fact calculates entire Rix map and taking into account also the final state effect. So really how the 4F level filling the 3D state, and then he does the cut and then reproduce the data. That was really beautiful, but what was next is, it was really nice that we do see pentavalent formation of the plutonium, but we of course wanted to know the speciation, what is really, which plutonium compound we do really observe. And here, in fact, the beauty of L3H comes to the game, let's say. So we measure the data at the plutonium L3H on that phase, and this is what you see here, the black curve. So this is also HERFD data, so also using spectrometer and L-alpha emission line. And then what Lucia tried, she tried simply to reproduce it by electronic structure calculation using randomness approach. So she takes different structures of plutonium, well-known structures, and then she tried to model it. And simply, she was looking at the correspondence between the post-H feature in experimental data and in theoretical. And in fact, I think we probed maybe 10, 15 different structures, and it was never working except only one particular case. And that was pretty interesting. On one hand, people say it's luck, but I don't think it's luck. I think if you really have the compound, so there are no other way to reproduce the structural shape of absorption spectrum if you take something else. So here you see the black curve. This is the data, experimental data, plutonium dioxide, and our intermediate phase. And the red curve, this is calculations from Lucia. So just by looking at the position of the post-H features, we were really able to find which kind of plutonium phase we form. So this is the mixture of the ammonia carbonate species, NH4, plutonium dioxide, CO3. And what was also pretty unusual, we just kept this sample for 3 months. And when we measure it again, and the spectral shape remains the same. So in fact, it means that that particular compound is extremely stable. So it could be really stable over the period of 3 months, and nothing really happens to it. Of course, we finished the synthesis until the end, when we really formed the plutonium dioxide nanoparticles. And by taking the data, we saw that, of course, the final state of the nanoparticles, they don't have any mixtures of oxidation state. It is only plutonium-4 compound, and very similar again to plutonium dioxide reference. But why this data was important, I mean, this experiment, let's say, at the synchrotron was important for chemistry of the plutonium. I mean, first of all, of course, we confirmed that redox transformation from the plutonium-6 really goes through plutonium-5 first and then plutonium-4. Then additionally, that kind of phase, intermediate phase, which we form pentavalent intermediate phase, this is solid phase. And for chemists, it's very unusual to see pentavalent plutonium phase, not a liquid phase, but really in the solid, which is stable over the period of 3 months. So that, of course, was something new, unusual, and that nobody saw before. And this is also, I say, a nice example how spectroscopy helped chemists to identify and create the new materials. And with that, I think I can stop again. Yeah, I show again here the covers because I'm really proud of them. I mean, working in this kind of narrow field of actinides, it's very nice to have opportunity to publish plutonium chemistry on the cover, I would say. So it means that still chemists appreciate what we physicists do for actinide science. So thanks a lot, and I will be happy to answer questions.
Very good. This is your second break, yes?
Yes.
Okay, I'm going to ask everyone to hold their questions and let you finish your talk because we've got about 15 minutes or so left, and I want to make sure you have a chance to finish the third piece.
Exactly. Thank you. It's not a lot. So
okay, very good.
I want to talk a little bit about selection rules and M4 versus M5 ages, because people generally assume that in principle M4 and M5, it doesn't really matter what you measure, because you excite from the 3D states, you probe exactly the same 5F states, and then even you can start to mix the analysis, but this is not really the case. And it's in fact was already done for the uranium system, but I show here the plutonium case. When you go from the 3D free half, you only reach one state, which is 5F 5 half at M4H. But in case of the M5, you already reach 2 states. And that, of course, complicates everything. So in principle, both transitions are not identical, so they're different. And you also see it in the experimental data. So this is the same sample recorded at the same time, at the same beamline, just at different absorption ages and using different emission lines, M beta and M alpha. And that's how different it is. So then if you start to look towards different components, you see that this kind of shifts, which we are looking at, plutonium-4, plutonium-5, that also became different. And why, in fact, I show here, so Sergey published recently a very nice paper, the review, where he reported the theoretical calculation and where he really discussed the difference between M4 and M5. So he reported were not only HERFD data, but also the RIX data, and goes even further. So he really talks about the final state effect in the HERFD data, because even if you do the cut, the final state effect will play the role, and he showed nice examples there. So if you are really curious, please take a look in his paper. I found it really fantastic, and I'm sure it will be used quite a lot in the future as soon as we start to measure more actinide materials like californium or whatever, and curium. Yes, so, and I want to talk maybe a little bit about the spectrometers and some kind of, let's say, instrumental point and resolutions. So everything what I showed today, I mean, almost everything was measured at ID26 beamline at ESRF. So it's my former beamline where I was before, which has Johann type spectrometer, 5 crystal analyzer spectrometer. And Peter recently published the paper, also nice review, in fact, about the capability and capacity of the instrument, and his history of development, how much was used, and what was community learned by having this spectrometer. And I would say that based on my experience, this is ID26 is still remain the best beamline regarding the intensity and energy resolution for actinide M45H spectroscopy. But in fact, at ESRF, in principle, almost all actinides can be studied by different methods, and this is really allowed, with certain limitations regarding the activity. But in fact, in Europe, we really have dedicated actinide beamlines, which has special license of having actinide materials with a really high activity levels. And I found it quite unique. So I put this slide here just to show you that all three beamlines, so it's first of all, it's a Mars beamline in Soleil in Paris. So when there is a Rossendorf beamline at ESRF, where I am for the moment, and there is a contact beamline in Karlsruhe. So, and all three beamlines can go down to the tender X-ray range, so we can really reach MHs. And the funny thing is that all three beamlines also have the spectrometers. So that entire, entire experiment, which in fact took place 10 years ago, more than 10 years ago at ID26, was so well received by using spectrometer and probe the MHs of actinides that in fact dedicated actinide beamlines start to look towards that direction and to go towards either pushing the incident energy of the beamlines to go really to the MH, like that was the case of the Mars beamline, because we have spectrometer, also Johann type spectrometer, which was already installed way before, but recently scientists were put really effort to go towards 3.5 Kev and reach MHs. And at contact beamline, there is a copy of spectrometer of ID26, so also 5 crystal analyzer spectrometer, exactly the same at Rossendorf beamline. We also have a copy of ID26 spectrometer, which we successfully use. And here is my last slide that I'd like to maybe discuss a little bit, or maybe to show you, in fact, what affects really resolution of M4H data. So I show here the M4H data for 3 compounds. This is thorium dioxide, uranium dioxide, and plutonium dioxide. So we don't talk about M5 versus M4. So this is only M4 recorded at the same beamline with the same spectrometer with the 5 crystal analyzers, one meter spectrometer at ID26. And in fact, just by looking at the numbers and values, you would realize that in principle resolution, the spectral feature will always depend on the several facts. All 3 compounds here, for example, so we're all cubic, we're all oxide, they have the same oxidation state. They have different number of electrons, 5f0, 5f2, and 5f4, and that you nicely start to see here. But at the same time, I mean, of course, spectrometer configuration is also different. So in case of thorium, I mean, this is the best Bragg angle, 79. The core hole lifetime, just by tabulated value, is also lower than for compared to uranium and plutonium. And I think that's why the thorium has the most narrow profile, which we recorded so far at M4Hs, if we compare to uranium and thorium. And in fact, why I show it, last month we did one test. So we tried to use half-meter spectrometer and compare to the data of 1 meter, just in order to have the flavor how the half-meter spectra will look like. And in fact, why do we do it? Is of course we gain intensity by going to the half-meter bending radius. And in fact, in case of thorium, even that the Bragg angle is 79, we really saw the effect. So you start to lose the sensitivity, and you hardly see this kind of post-H features which you observe here. Which was not so dramatic in case of the uranium. So we didn't probe plutonium yet, but in uranium, at least the feature and the sensitivity was still there. I mean, definitely it was broader, but I didn't find it so dramatic like for thorium. So that's, I think, a nice example shows that in principle, it is matter which kind of instrument you use, what kind of spectrometer configuration you have, if you really would like to understand tiny features and tiny changes in electronic structure. And with that, I just want to finish by acknowledging, of course, people who make all this work and without whom it cannot be done. That's, of course, the top group at the Rossendorf beamline at ESRF. And I also would like to acknowledge Sergey and Peter, in fact, with whom we started to do first experiments on the M4Hs. and we still go on. So we still collaborate and go towards plutonium now. So that was a really nice story. And I didn't talk a lot about the chemistry now, but definitely it cannot happen, all these studies, without excellent chemists from Moscow State University, who really synthesized not only nanoparticle materials, but also all references which we studied at the beamline. And of course, without our laboratory in Dresden-Rossendorf Zentrum, which we use for synthesis of materials, of actinide materials. So in fact, we synthesize them in Germany, and when we bring it to France for the measurements at the beamline, this is how it works. So thank you for your attention.
Very good, thank you. This is a great talk. As people type in their questions, I'll start off with a few questions. If you go back to that last slide when you were talking about the 1 meter and half meter analyzers, whether let's say at 1 meter, what do you think is the dominant contribution to the energy resolution, to the broadening of the spectrometer?
I mean, I would say it's you mean that it's of course combination, like thorium, you know, is also low in the energy, in the incident energy. It's 2.9 versus 3.7. So already the incoming incident energy resolution is better. But additionally, the Bragg angle of 79 degrees is of course helping quite a lot. Plus, as I said, you know, because we have 5 F0 electrons, so this is also not the case as the case of the uranium, where you would really have this kind of interatomic interaction of the 5F state.
Well, sure, but that's not instrumental.
No, exactly, no.
Right,
but,
right.
Okay,
where I was
I can even have, but by the numbers, I would say the best possible resolution for thorium dioxide at M4H, if we measure elastic peak, and when we take half Vs, half maximum, it's about 400 millieV. And for the uranium, it's also 400 millieV.
Yes,
so,
yes.
I mean, it depends. Yeah, Peter have a nice instrument with a slit in front of the detector, so that also helps in the resolution estimation.
Right.
With plutonium, it's worse. I think it's 0.8, if I remember correctly.
Okay.
But definitely, I mean, it's combination of incident energy and the Bragg angle, right? Of the. But
sure. So you have both source size effects and also Johann effects, of course.
Exactly.
Right. When you went to half meter and everything got bad, was it Johann, the fact that you're twice as wide? Did you try slitting the sides and maybe you can still use the up down?
We tried a lot. And I should say it. Okay, it was only one test, but we tried a lot. In fact, the beam size it became even smaller. So for 1 meter, we have about 150 microns vertical direction, and the scattering geometries we affected only by vertical size of the beam. With a half meter, we slit it. I mean, it was possible to make it even smaller. So it's about 50 microns. So 3 times less.
Yes.
Analyzers, both analyzers were done with the same company. It's XRS Tech. So I believe, yeah, I couldn't judge here if the quality of the analyzers were different or the same. And the Bragg remains the same, right? So, I mean, that's why I don't know. I mean, for me, it's really the fact of yeah, it's really fundamental, right? If you want to go to improve even better resolution, you go to the 2 meters, which maybe we have to try.
Yes, or flat crystal with very small beam, completely unstrained. Okay, I'm looking for.
Is it anyone did it with a flat crystal?
Yeah, we did a little bit with the 3D printed plastic spectrometers. You can make an array of flat crystals, and if you have a focused beam, a small beam spot, you just disperse the reflection on a big enough camera. We did that at 20 BMs some years ago. I don't remember specifically for uranium image. I'm suddenly forgetting if we got around to publishing it or not. But it works, and you get a very, very large solid angle. But you have to work hard to reject stray scattering inside the spectrometer.